and if we start with just mechanics, we're concerned with the state of rest or motion of an object or body. Okay? So we're dealing with an object or body. So in this class, we're going to deal with two types of bodies. One is a particle, and the other is a rigid body. So on the particle, you can think of, even if I had a wheel or a hoop, that I'm dealing with the idea that I can track the center of mass, okay? Because we all know, if I was in good old physics class and I had my book, even though it's hanging off the edge, as long as my center of mass is above the edge of the table, the book's not going to fall off the table. It's when that center of mass creeped over the edge that I was going to get the book to fall off the table. So the thing about it is I really want to be following as a particle. So as a particle, I'm kind of tracking as a center of mass. So you can kind of think of it this way. If I'm looking at the solar system, there's the sun, and here's the Earth. Because of how far away the Earth is from the sun just sees the Earth as a speck. And so that I can look at it as a speck, and I can be dealing with it as a particle. So the first sections of these chapters, we're going to be analyzing motion as if something were a particle, because we're going to do that particle part. The rigid body starts taking into account that I've got an object that is going to have some size and some mass to it, some sort of volume, and the size of the object is going to come into play. We can do a couple of different things, like what we did in statics, where if I have my water tower I have a shell and a vessel and a funnel coming down here, I could do those three pieces. But now if I'm starting to put this into motion, I gotta worry about things a little bit. I gotta worry about other aspects of what's happening that I didn't have to worry about before. So we're going to be looking at, and the thing about a rigid body is, think the wheel on a railroad train, okay? I don't get a change in shape. It doesn't deform. So if I push on it, I still am going to have a wheel. So if I think of my big rail wheel, it's not changing shape at all. It's not going to deform. I'm not losing anything into that deformation. And so that's one of the things that we're worried about from a rigid body point of view versus the other. What's going to happen to you as you go forward is the next class. It's like fluid dynamics, where I no longer have a rigid body. Things are going to move, things are going to spread out, things are going to have a different aspects. So we're worried about particles and rigid bodies, and we're starting. So in statics, just to remind everybody, because I'm not sure when everybody is where we are. So in statics, our object is usually at rest, but it could also be in constant motion, provided there was no acceleration. So if I looked at it, we had the sum of the forces. Remember, forces are going to be a vector quantity, was equal to the mass times my acceleration, equal to 0, and this was our first condition of equilibrium. Our second part of it than it is in the engineering part, and we used M, right? And we used D, so I'm coming back to the physics part of it where we talk about torque. And remember, in torque, this is my moment of inertia. And this is my angular acceleration. and that had to be 0 as well, whereas this was a vector quantity and that was a vector quantity. So even though we ended up dealing with the moments and we simplified things a lot, it comes back from the fact that if I have torques, I have that angular acceleration, and as long as I'm in statics, as I had no acceleration, I could still be in constant motion. I just can't have an acceleration. And that's where we were, and this was our second condition of equilibrium. So we have that piece. Now, other thing we have to worry about, and this is going to come into play that we didn't play with it quite as much in statics, but we were going to start playing with it. Remember that torque, which gave us the moments, is related to R cross my vector quantity. So we're going to have to recall our vector aspect of various pieces. And so if you haven't reviewed cross products in a while, cross products are going to be in Appendix D or Appendix B. It's in the Hibbeler static section 4.2, but it's also in Appendix B. So you've got a place to go back and look at the cross product aspect of things. So that kind of gets us the differences between statics and dynamics. Okay, we're all going to be off of the chat for right now. I was just making sure it worked. Days going forward, but we'll get it going. Typically, bring them in accelerated motion. Potentially. So, and we're going to do like we started back in engineering physics. Okay, remember in engineering physics we do it in two parts. We started out with kinematics, but we didn't care what was causing the motion, right? We didn't knew we had motion. And if you guys remember, that gave rise to equations like this: v squared is equal to v in position. We had v is equal to v initial plus at, and we had a change in position which is equal to v naught t plus 1/2 at squared. And we ended up we derived those equations. We also looked at the difference between instantaneous and average. Instantaneous gave us our limit as t was approaching 0. And I will tell you right now, depending on which dynamics book you pick up, Hibbeler doesn't go into this as much. I have 3 other dynamics books that really start with the limit for the instantaneous part. They really go back and look at that aspect. They're actually going back and teaching it from a more vector analysis. Our book, he's actually just jumping right into problems, okay? And he's expecting you to remember that, okay, I have an instantaneous and I have an average, and recalling that particular aspect. So we do want to look at that piece. And then we're going to start with the kinematics, and then we're going to go to the Newtonian, where what's causing the motion, what are the forces that are involved, and we're going to make that same progression that we did in engineering physics. So let's kind of go back, and I'll get you a couple of definitions just so that we have the definition. So by our author standard, a particle has mass, but the size can be neglected. and the geometry of the body is not involved in the analysis. A rigid body is made up of a combination of particles. At a fixed distance from each other, and the shape does not change. So that's our difference between a particle and a rigid body, and we're going to start with particles. We're going to start with particles. And our book gives us a problem-solving strategy. First is read the problem. And in this one, as we start progressing through the book, you're going to want to be making some choices and some analysis. You want to look at it as what's happening. And in this case, it's specifically looking at it as a particle going to work? Is a rigid body going to work? Is my coordinate system going to work? And then, as I always say, draw the picture and label. And include things like the not specified knowns. Specifically gravity. And if we are in meters per second, you want 9.81 meters per second squared. If you're in gravity in the English units, you're going to use 32.2 feet per second squared. So that's one of the things that you got to kind of look at and make sure you've got those pieces. And this was, so as I'm doing this, and finally at 3, after you've drawn and labeled, you've got to commit to your coordinate system. Then you want to look at what principles might. And even though we just started out with those 3 equations that we used all through physics, you're going to find that now we're going to throw a lot more calculus in it. And not only are we going to throw a lot more calculus in it, we're going to manipulate the equations a little bit more. And that's where I said I'm a little rusty, because I haven't had to do it in a while. So you're going to have to, if you've got your calc book, you may want to have access to it. Because you may want to go back and look at a few things. I've actually, in my notes, as I've started pulling my notes together for the class, I've gone back to the mathematical principles to say, all right, let's go back and look at the mathematical principles, because we're going to have to apply them here in the physical problem that you may or may not have had to do before. When you're running the calc problem, you're just running the math. When you're running the physics problem, you've got, well, I've got my equation, I can plug it in. Well, now you're starting to get a little bit more complex, and so we're starting to get into those mathematical methods that you may not have done a little bit more. Then you have to define. Now, they recommend, and this is one of those strong cases where you're going to have to make a decision when you cut and run, is you want to take it as far algebraically as you can. And you're going to have to decide, because you want to solve to plug in and you want to watch your units. And the unit analysis is going to help you out. It's going to make sure you haven't made a mistake along the way. You want to watch significant figures and kind of how you're going to carry those through. Ultimately, you're going to solve, and then you're going to question, does it make sense? And luckily for us, this is a case where, because we are using mastering, mastering's going to tell you pretty quickly whether or not something makes sense or something doesn't make sense. It's gonna give you a or not, and we're gonna be looking at where things are. And I will tell you already that our book does something that's gonna drive us all nuts. Okay, I don't know why he's done it this way, but he has. So we're diving in. And we're looking at going back and saying position. Remember, position is going to be related to where am I? And displacement is my change in position. So remember,